What are the chances? In our next section, we'll look at some of the review exercises for Chapter 13. We'll do some simple applications of probability, and this will help us get a better feel for the topics introduced in the probability lecture, namely the conditional and unconditional probabilities, independent events, and the multiplication rule. Our first question is a true or false. If something has a probability of 1000%, it is sure to happen. Well, an alarm bell should be ringing for you as soon as you read this item A, because as we just discussed, only chances or percent chance probabilities can only range from 0 to 100. So if something has a probability of 1000%, it's impossible because that's not even a possible probability. So this one is going to be false. Now let's look at B. If something has a probability of 90%, it can be expected to happen about 9 times as often as its opposite. This is true. Remember how we discussed that the probability of something happening is 1 minus the probability of the opposite thing happening. So the event will happen about 9 times out of 10, and the opposite event will happen the remaining 1 time out of 10. E for event happens. Nine times out of 10. The event of not happening is going to be the other 1 out of 10. So this is, of course, officially true. In our next problem, we have 4 cards that will be dealt off of the top of a well-shuffled deck. Let's remember, a well-shuffled deck can be assumed to be or represent a random assortment. There are 2 options. We need to choose which option is better. 1, to win $1 if the first card is a club and the second is a diamond, and the third is a heart, and the fourth is a spade. Or to win $1 if the 4 cards are of different suits. Are these options the same? No, they clearly aren't, because in option 1, we have the cards coming in the following order. The first one needs to be a club. This is a bad club. Assume that's a club. The second must be a diamond. The third is a heart. And the fourth is a spade. The point being here, not that I shouldn't become a cartoonist, but that these, in option 1, the suits come in a particular order, and it's not just their 4 different suits, they have to follow this order. In option 2, they just have to be different suits, and they could come in any order. You know, we could switch up any of these. Thus, option 2 gives us a lot more ways to win. We could go club, diamond, spade, heart, you know, many, many options. In problem 5, we have a ticket drawn at random from a box. And looking at this box, are color and number independent? Well, to examine this, it's nice if we think about some of the options for our outcomes. If only one ticket is drawn at random from the box, so we can see that there are 2 chances in 3 to get the number 1. Number 1 occurs 4 out of a total excuse me, of 6 times. We can reduce this to a 1/3 probability, a 2/3 probability, of course. And likewise, there's a 1 in 3 chance to get 8. So 8 occurs 2 out. We get the number 8. Let's move it down here. We still have 6 possible numbers to be drawing from. 8 occurs twice. 2 out of 6 is going to reduce down to 1/3. And you can see those chances sum to 100%. And it's the same if we look at the white-black division. Half the tickets are white and half the tickets are black. So for either black or white, there's going to be an independent chance of getting 3 out of 6 or 1/2 for either, and it's completely independent. Color and number there's the same color and number options available, and they're completely independent of each other. Let's go ahead and move on to number 7. In this problem, a coin is tossed 6 times. We have 2 possible sequences. You can see them in 1 and 2. And these represent the order given. So these would land heads, tails, tails, heads, tails, heads, all heads in a row. Which of these observations is correct? Is sequence 1 more likely, sequence 2 more likely, or both sequences are equally likely? This problem is getting at a common misconception that there's a difference in the likelihood of either of these outcomes, but in fact, both sequences are equally likely. Because the reason this is true is that the chance of getting heads or tails on any particular toss is always independent. There's always an equal chance of heads and tails, and they're always independent. So if we thought about this in just another possible question context, we could think about these as true-false questions. Sequence 1 is more likely, that would be false. Sequence 2 is more likely, again, false. They're equally likely, this is the only true statement. And the likelihood of either of these sequences is 1 out of 2, the chance of heads or tails on either roll, times, or to the power of 6, because there's 6 events. We could visualize this by just remembering we're multiplying these independent events together, and they each have the same probability, which is why we just raise it to this exponent 6. Now, let's think about a die. It's rolled 10 times, and we can look at the chance of getting these different outcome scenarios. In our first scenario, we're looking at getting 10 sixes. Again, each roll of the die is independent. It doesn't have any relationship to what you see on the next. And each time you roll the die, there's a 1 in 6 chance of a 10. So if we want to get the probability of rolling 10 on all, or rolling 6 on all 10 trials, then just like in the last problem, or the last example, we can take the probability of getting a 6 on any particular trial and rise it to the exponent 10 because we have 10 trials. And we can just use this exponent shorthand because, again, it's the same probability of being the 6 across. Now I could write this all out. This is equal to 1 6 times 1 6, on and on, to 10 trials. And if you work out the math on this, the 10 to 1 6, this is a very small probability here. It works out to 1 out of 60,466,176. So a very small probability of getting all 10 sixes. Now, when we look at B, we can examine the probability of not getting 10 sixes. The process for doing this is, as we discussed, the probability of not getting any of something is the 1 minus the probability of the opposite. So we can take 1 minus the probability of getting all 10s, or all 6s on all 10 trials, excuse me. So 1 minus 60,466,176. This is a minuscule number, and we would say that it's approximately 1, equal to 1. So it's most of the time the absolute, beyond vast majority, there's just an infinitesimal chance of getting all 6s on all 10 of your rolls. So the probability of not getting 10 6s is about 1. And finally, when we look at part C, we have all the rolls showing 5 spots or less. When the rolls show 5 spots or less, this could occur on the probability of this is 5 out of 6 on each roll, because what we're looking at is the spots showing, or it's showing 5 spots or less. So there's 5 opportunities, 5 out of 6 times it'll happen. So to get this probability, just as we did in the first one, we rise it to the exponent of the number of trials. And again, we can write it out like this, but here's the shorthand, so this is going to be equal to 5 6 times 5 6 over and over for each trial. And it works out to be about 0.16 or 16%. Oops. And this last one, it's really just a thought problem. You're not going to see anything like this one on the exam, although you might see problems similar to some of these earlier ones we did. But in this one, just thinking it through, in the box shown below, each ticket should have 2 numbers. A ticket will be drawn at random. Can you fill in the blanks so the 2 numbers are independent? Yes, we can. And in case you work this out, they would follow the following pattern. Or they would not follow a pattern, but they would, it would work out like this. And I'm just giving you the answer here. I'm not concerned about figuring out the work on something like this for our exam, and I know all of our time is limited. So, if you want to discuss this one more with me, I'd be happy to in office hours, but suffice it to say, can you fill in the blank so the 2 numbers are independent? Yes. And this is how they work out. In review, we covered a few different types of probability problems, and let's look at the ones that you should be, generally comfortable with for your exam. What ideas from here are going to be the takeaway points to remember for the exam? Well, first is that very first topic we discussed, which is that if probabilities only go from 0 to 100. So any probability that's outside of 100% is impossible. And certainly the idea that something can be expected about as many times as often as it's a 1 minus its opposite. Simple thought ideas like this, which of these 2 options gives the best probability? This is a great simple application of some of our probability problems. Also recognizing which sequence is more correct here, or evaluating statements like this to see if they make sense. And a problem like 9 is probably as complex as we'll get for anything from chapter 13. And may the odds be ever in your favor.